Okay. Columns. Now, I know that you've been studying every inch of this handout since I gave it to you last time. And you have it memorized, right, and can regurgitate every detail of it to me. So that's why we're going to spend some more time talking about it today, right? So we can all kind of bring everyone back up to speed, everyone again on the same page, kick things off in the column world in a good shape. Now, when it comes, so we'll hit some highlights early on some things that should be realized. Now, there's one parameter that determines everything about column behavior, whether it crushes or whether it buckles. And what's that parameter? Does anyone remember? KL over R. It's all about KL over R. KL over R is low versus high. What's low versus high? Well, that's what these calculations are going to do, right? That's what these calculations, which I think we didn't quite get to last time, but we're going to kind of cover the packet in a different way this time, okay? A little more holistic way, a little more way with you basically assuming you have an understanding of some of the stuff we talked about before. But if you recall, this is the chart that tells you everything. It tells you whether your column is going to be on this plane or on this plane. Okay? Whether it's going to be on this curve or on this curve. And this is the way I've got it set up is pretty straightforward. You calculate your F Euler capacity, which depends on KL over R. You can compare that to your yield capacity, and if it's greater, F Euler is greater than 0.44 Fy, you use this equation. If your F Euler is less than or equal to 0.44 Fy, or pardon me, just less than 0.44 Fy, you use this equation. This equation is basically you're using your F Euler equation, you're just putting a couple safety factors in front of it. You're putting this is your phi factor, which is 0.9, and this is an imperfection factor, a 0.877. They're assuming a certain amount of imperfections. Okay? So basically, if you build your columns to meet AISC out of plumbness, then you will meet these assumptions, and you can use this safety factor. If for some reason you would suspect that your column's been beat up, it's been hit with some stuff, and you hammered it back in place, or wasn't built as per AISC specifications, you might want to consider using a lower safety factor, right? A lower number, a lower reduction factor, right? A higher safety factor than 0.877. There's sadly no guidance at all on that, but it is what it is. It is what it is. Great. So KL over R, that's cool. And typically, historically, we say we either have crushing or we either have buckling. But we realize as we learn more and more and more, it's not that easy. Okay, it's not that easy. It gets a little bit more complicated because of imperfections, residual stresses, uneven loadings, things like that. It's not as easy to draw such a line. Great, talked about that. Talked about this last time in the P delta effect. Talked about this F Euler equation, what all the different things were. What was K again? Effective length or the end restraint factor, right? So for a pin-pin non-sway column, what's K? It's 1. It's 1. Okay? L, that's the length between your supports or your braces. R, what's R? Radius gyration. About the axis that it's bending. And we usually are going to check columns to buckle about 2 different axes of bending, because you could think of it as a KL over R in one direction, we have a KL over R in the other direction, and which one's going to control? The larger KL over R. How did I know that? Look at the graph. Look at the graph. Remember, I can have a K, an L, and an R, and they can be different depending upon the axis that it's bending. Okay? And the larger K over R is going to control. The larger K over R, if everything is going to follow this equation, the larger K over R is going to have a lower sigma critical value. Awesome. We got pi constant, and that's just this effective length factor, KL. Okay, and I say, hey, why? And then I have this. This is what the actual test data looked like. This is what actually happened, and this is what mathematically should happen. And why is there a difference? Imperfections, residual stresses, uneven loading, which in effect are all imperfections, aren't they? It's all imperfections, but residual stresses and imperfections are two different beasts. There's imperfections over the length, out of plumbness, out of not being straight. There's then there's uneven loading, and then there's then our favorite residual stresses that come from the rolling process. We started to talk about this K factor and what it really means, what it's all about. And we said, hey, Euler, this great guy, derived the buckling for a pin-pin column, and people started to do a bunch of other differential equations after him to find what all these other columns looked like, and they found the engineering solution will say, hey, you know what? We have a basically equivalent pin-pin columns in every one of these other problems. Equivalent pin-pin columns. And so what we're basically doing is we can turn this into an equivalent pin-pin column with half the length. We can turn this into an equivalent pin-pin column of 0.7. It's actually root 2 over 2, but it's close enough to 0.707. Okay? That's what the K factor does. That's what it's all about. That's what it does. It takes a complicated structure, and these aren't even complicated. You ain't seen nothing yet. It turns it into something that's like, we know how to solve and it's easy. It's a KO1. And it does a pretty good job. Now, I think I showed you this last time. And this is really, really similar to a table here that's in the 13th edition. It's a pretty close table, a pretty close page to that on the 14th edition. I have recombobulated the table in a new way because mine is better. Way better. Okay? And I don't know why the world doesn't see it the same way as me. They will someday. Right? Maybe you guys can go out there and help change the world, right? To make it see it in a different way. But I feel that you should organize that table in terms of no sway on one side and sway on the other side. I also feel that you should organize the table starting out with our pin-pin column and getting more and more and more stiff from there. And starting out here from our fixed column and getting more and more and more free. Okay? So we're moving in stiffness. Okay? We're moving in stiffness from one side, from here to here, basically. I think that's a more obvious way to explain this stuff. And probably what happened was the first person that wrote the paper that used those columns, those tables in it, put it in that same order, and it got slapped in the steel manual in the same order that was the paper, and it's never changed. Okay? That is not a good reason not to change, okay? When things make sense to do things differently, you should. So this is great and cool and neat and fun, but sadly not all problems when it comes to columns can be solved using one of these things. These are great, though, to help you get a feel for where you're at and how things change, okay? Great to kind of, so if I have the best I can possibly be in a sway structure, the absolute best is a KO1. If I ever find a K less than 1 in a sway structure, something is wrong. Oh, how do you find the difference between sway and no sway? Can the top move with respect to the bottom? Can the top move with respect to the bottom? And the answer is, this is a block in air. So yes, it can move. These cannot move. Okay? But it does usually come down to bracing. It does usually come down to it leaning against a wall in real life, typically. So these would be sway structures. These would be non-sway structures. So if I have a sway structure, my K can never, ever, ever, ever get better than 1. What's the worst it can possibly be? What's that? I don't know. Infinity. Infinity. What's the capacity with a K of infinity? What? 0. How'd you know? Go back to the table. Oh, remember the graph that I said is the secret to everything? When K gets infinity, what's this turn into? Infinity, right? So what's this going to asymptote to? Just keep drawing on the chalkboard, right? Over and over and over again. It's going to get to 0, right? Yeah. Okay. Cool. Cool. Now, when you come to no sway situations, your K has to be between 1 and 0.5. Has to. Has to. So, if you don't get an answer between 1 and 0.5, you've done something wrong in a no sway situation. Now, when we get to actual structures, because these things, I mean, come on. A block in the air, I mean, and I think I said last time, and I'll say it again, because it's just so true. Only architects would ever build a block in the air with nothing on top of it, right? Everyone's saying yes. That's right. Okay, but how about this? Do we ever do this? All the time. Flagpole problems, right? These are flagpole problems. Okay, and I think this would be hard to do and build in real life. You'd have to make this like massive. Because it's just going to rotate, right? I mean, a lot of things, if they're not very heavy, they're just going to rotate. And you have to build something massive to get it to not move. Okay, onward to things that we actually care about. Actual structures, things that look something like this. And when we come to things like this, we still ask ourselves the same first question. Is it sway or no sway? No sway in this case. But we're going to change. We're going to turn all of these beams and columns into, a spring. And we do that with our friend, the alignment chart. Right? Do that with our friend, the alignment chart. Which, if you haven't used the alignment chart, oh baby, get ready. The fun is around the corner for you. So, we've got an alignment chart here, and we've got an alignment chart here, and we're going to talk way more about alignment charts coming up. Then, I introduced the equation. Oh, we've seen that earlier today. That's awesome. Start working some example problems. Oh, yeah. Before I introduce the equations, there's a table 422 and a table 41. If you've never used those tables before, you should look them up. They're really useful, extremely helpful. Table 422 is the one that people like to use because the only thing you need to know is KL over R and Fy. That's all you need. KL over R and Fy. When it comes to table 4.1, that's the one where it's solved for, theoretically, all you need is KL. And it only works for an Fy at 50 KSI. That's what all those columns are derived for. It's for an Fy at 50 KSI. Okay? Theoretically. But it's not quite that way. KL is derived with respect to the least radius of gyration. You're not dealing with the least radius of gyration. You have to trick this one. And I do that in a future problem. If you've seen that before, great. Review it. Make sure you know it. If you've never seen it before, read a book. Now, what people inevitably end up doing is they end up using the equations because the equations always work for anything I throw at you. Or they use table 422 if the Fy happens to be in there. If it's not in there, then you got to use the equations. Great. Now, I work an example problem here. I'm not going to go through it or talk much about it in class, but what I want you to see is the method. First question I ask, and this is the simplest problem you'll ever work. Okay, it truly is when it comes to column buckling, and we're going to work up very quickly to some very hard problems. Okay, but you're going to use the same method every time. You're going to ask yourself, sway or no sway? You're going to answer that. And it could be different in different directions. Not for this problem, though. Depends, actually. We won't go into that. K of 0.7. KL over R. You're going to find KL over Rx. You're going to find KL over Ry. You're going to figure out which one controls. Okay? You're going to find out, oh my gosh, KL over Ry controls 36.9. Since it's larger, I know it's going to control. And then I've worked the problem 3 different ways. You do not need to work every problem 3 different ways. If you want to, great, but you're wasting time, and time is money and points, but that's fine. I worked it with the equation. I worked it using table 4.1. I worked it using table 4.22, and I got answers that were all really, really close to one another. Why aren't they dead on the same? They're like 0.5% difference. Okay, that's like within rounding error. It's not that big of a deal. Awesome. I try to make the problem a little more complicated by restraining it in one direction and forcing it to fail in another direction. Then I go and work more fun. I say, hey, let's actually get to a frame. We have frames. Now, in this class, whenever I draw a circle at a joint, what does that mean? A pin. Sometimes there'll be circles at joints. Sometimes I'll just draw a circle at the beam, and the joint will look like that. What does that mean? That means that's a pin. That beam has a pin connection at the end. It means that beam has a moment connection at the end. So in this direction, there would be a moment connection. In this direction, it would be a pin connection. You must start thinking and looking at things in 3 dimensions when we go to work these problems. But again, I work them all the same. I asked, is it sway or no sway? I find my K's. I find my KL over R's. I find my capacity. Same. Change my bracing scheme. Changes my KL over R's just a little bit. I get a capacity. And then I ask the fateful question, what would happen if we removed a brace and used a moment connection and said, hey, that looks just like this, doesn't it? That's the same thing, just rotated. So that is saying, this is important, that in this direction, we have a sway frame. And in this direction, we have a no sway frame. That's what we're up against here. That means for this column, in one direction, I'll have different K's. I would expect to have different K's, depending on what's going on. How do we solve problems like this? Well, we go back and look at our table. Where's our table? Oh, okay. I'm looking for the one that looks like this. I think it was pinned at the bottom. Which one is it? This is sway, so it's got to be over here somewhere, right? Which one is it? What's this one, right? No! No! This assumes infinite stiffness at the top, doesn't it? Infinite stiffness. We don't have infinite stiffness. We have a beam. When we have a beam, we have to work it as if it's a rotational spring. It means we have to use our friend, the alignment charts. And that sets us up to stop right here. To go turbo speed. Next time, don't expect a review. Much of a review. I never give you much of a review, right? They're always awful. But don't expect a good one next time. So, see ya.